So for today's class, we are going to finish off this chapter, chapter 11. I've literally just I was writing an end of year report to kind of give me an idea where to start next year. So there's a couple of experiments here that we would have done in class, and I think it might be nice that if we're all back and everything's normal in September, please God, we will start with this. So even though you'll have done the theory, we'll actually start in September with these, it's called separation techniques. And we'll start with these separation techniques. I think that might be a nice way to start the year. It means your first couple of classes will be practical, which is nice. So what I finished today, that's up to that is what's testable. So I think on your list I also had chapter 15. I can't remember if I don't think I put chapter 6. Like, we basically 2 chapters left that we were supposed to have finished this year, which is, like, I'm delighted with that, because when we broke up in March I thought it was going to be a lot worse than that. So we're doing great, and we'll definitely make up 2 chapters like over 2 years. There's no problem with that. So up to chapter 11, as in that would be the last thing testable. All right. Okay, so separating mixtures, there's a few ways, and there's some that you would have done as in experimentally, and there's some that you would not have done experimentally. Okay, so we've already talked about mixtures. We know that it's 2 or more substances are physically mixed together. And if you remember, one of the characteristics, or one of the things that differentiated between like mixtures and, do you remember we talked about molecules and compounds? So one of the big differences between mixtures and compounds was that one can be easily separated and one cannot. Okay, so a mixture could be easily separated. So how do you separate? Okay, so I realise I messed with the numbering here. I only did that because you tend to do these 2 together. So filtration is used to separate insoluble solids from liquids. It involves using a material that allows only liquid to pass through, but not solid. So I mean, I don't know if any of you would have used coffee filters or anything like that, but that's the idea. So you have you have your funnel, and then you lay in some filter paper. Now there's scientific filter paper, as in you can buy it in the scientific suppliers, but there's also coffee filters, and they're pretty much the same thing. Okay, and the idea then is here you have your liquid, and you have an insoluble solid. Okay, so that means that the solid is not going to dissolve, it's just going to sit. So when you pour this in here, all the solid bits get caught in the filter paper, and going through into the beaker is just going to be the liquid. That's filtration. Okay, big thing with these is they all have a purpose. Okay, so I mean, I think you could describe filtration, don't have an issue with that, but what does it separate? Insoluble solids from liquids. Okay? And then another one that we normally look at, this one I'll show you in the experiment, is to separate a liquid from a soluble solid. Okay, so this is evaporation. I'm going to scroll down and talk about another one now. Okay, so if you put like salt, yeah, that's the one they use. Look, that's the one I would have used in class. What did they use up here? Using filter paper. They don't give an example of filtration. Separating sand. Okay, yeah. So we probably would have done sand or soil or something like that. Something separates nicely. Okay, so here what we do is, so you'd have a beaker. Okay, and in the beaker you put water, and then you'd add in salt. Okay, not much salt. You don't want to end up with salt granules or anything like that. Just enough salt that you haven't reached, remember we talked about saturation point? So you haven't reached that point where there's too much salt to dissolve. You want it all to dissolve, okay? Shake it up. So you mix it around, literally like, sorry, I'm doing it here as if you can see me, but swirl the beaker. And then you pour it into an evaporating dish. Now you don't need to do that bit, but it's just, I suppose, they're designed to that. I mean, technically, and I actually think in the video, they don't apply heat at all. they just allow the water to evaporate over like several days. Okay, so do you remember we talked about that with evaporation and boiling? That the kind of um, particles or molecules within the water that have the most energy, they will kind of break free and become a gas, and then the next layer, and then the next layer, and the next layer, like the way a puddle dries up. So you could just literally wait it out and allow the evaporation to occur. If I was in the lab, I would probably get you to heat it because we want to do it in like 20 minutes. Okay, so if you do that, an evaporating dish is better than using the beaker, simply because when you do it with a beaker, the salt gets encrusted onto the beaker and it's pretty much ruined. Whereas on an evaporating dish, that's what it's designed for. It's designed to evaporate. Okay, anyway. So, evaporation is used to separate a liquid from a soluble solid. So essentially what we have is we've put our salt into water and you just have this solution of salt and water. Okay, if you leave it stand, the salt is not going to fall out, it is dissolved. Okay, so you pour it into your evaporating dish and you heat it. And what will happen is the water will boil and evaporate off solvent vapor. So I'm assuming this is water and salt, so the solvent is water. So that's water vapor, steam coming off there. And then what's left behind when you're finished is the salt crystals. Okay? So that's evaporation. That's a way of separating an soluble solid from a liquid. Now, the only drawback of evaporation is that there were two things. So there was salt and water. And in the process of evaporation, you do separate them, but you can only keep one of them. Does that make sense? So in your evaporating dish, we keep the salt, but the water's gone. It's been turned into gas and gone. Okay, so I separated them, but I couldn't keep both. There is a way of keeping both. If I just, we'll play that video now in a second. Okay, so no, it's not going to work. So essentially this thing here, it's called distillation. Okay, so if you look, right, over here, can you see where I'm pointing over here? We're heating it up, we're doing the exact same thing, okay? So, I mean, even if this, usually you don't use this for salt and water, you'd use this for two liquids, but I suppose you could. I don't know why you'd want to, there'd be no reason. But anyway, let's say, right, the difference here is when you boil and the water starts to evaporate, it can't leave. So what happens is it goes up, it goes down through this thing, which is called the Liebig condenser. Condenser. Okay, do you remember the word condense? That turns it from a gas back into a liquid. So you do the same process of evaporation. You get the water to boil and it boils off up into the Liebig condenser. The Liebig condenser turns it back into a liquid. So now what you've done is you've separated them, but you have both. Yeah? Okay, so a Liebig condenser, we may as well keep talking about it. So distillation using the Liebig condenser is used to separate a liquid and a soluble solid. Okay, so you could do it with salt, or separating two miscible liquids, and miscible means that they mix. Okay, so I would never use a Liebig condenser to separate salt and water. For reasons, you'd never get the salt out of the bottom of the round bottom flask over here. But you could, okay? It is a process. So the difference there is that, hopefully you understand that, is that it's the same process as evaporation, except instead of just letting the water boil off and become gas, it goes up into the Liebig condenser. A condenser turns the gas back into a liquid and you save the liquid. So if we were doing this with salt and water, you would have the salt here and you would have the water over here. So they would be separated and you would have both of them. Okay? The second thing, they're the two miscible liquids. They do that based on boiling point. So if you look for any alcohol in your house and you look on the label, no, I mean like vodka, or I'd say it's probably on like gin or whiskey, or I don't know if they just, anyway, you'll see on the front of the vodka bottle that it says like triple distilled and stuff like that. So they do this um, to purify alcohol. So essentially what they do is you have, if I just remove, sorry, that highlighter. So, okay, in here you would have the mixture of the alcohol and the water. Okay, you apply heat. The alcohol has a lower boiling point. Okay, alcohol boils at about 78 degrees, which means once you get to 78 degrees, the water won't have started boiling yet. Now, you may have had some evaporation because we know that that happens at any temperature, um, but it won't be boiling, so it won't start to evaporate. It won't evaporate as a whole. Okay, there may be some parts of it evaporating, but it won't evaporate as a whole. But it's 78 degrees, so the water needs to get to 100 to boil. But at 78 degrees, the alcohol will boil. So it will go up here as a gas into the Liebig condenser, which will turn it back into a liquid. And then in here, you get the alcohol minus the water. Yeah? So then over here, that will have gone, so you'll just have the water. Okay? Now, the reason they do it 3, 4, 5 times is because, like I said, this won't be absolutely pure. There will be some water in it. So you then take this, put it back in here, distill it again. Now the alcohol is even more pure, and so on and so forth. And it's just it's a purifying process. Okay? Right. So, first one is filtration. That's separating an insoluble solid from a liquid. Okay? Something that doesn't dissolve. Evaporation then can be used to separate a soluble solid from a liquid like salt and water, but you will lose the liquid. Okay? If you want to keep the liquid, you use a process called distillation. And that uses a piece of equipment called a Liebig condenser, so that when the evaporation occurs, so what's happening over here, up to that point, is just evaporation. But now here's the difference. This is stoppered, so the steam can't get out, goes into the Liebig condenser. It is a condenser, so it turns gas to liquid, and you get to save that solvent that in the evaporation just boiled off. Okay, so this will work for something like salt and water where the solid dissolves in the liquid, and then it will also work for two liquids mixed together, providing the two liquids have different boiling points. Because as you heat it, the one that reaches the boiling point first will boil off, go into the condenser and turn to liquid. And the one with the higher boiling point, which hasn't quite reached its boiling point, will stay here. Okay? So the Liebig condenser, we do actually do, but I do it. Okay, so it's quite a kind of complicated little apparatus to set up, and it's quite dangerous and it's quite hot. So normally what we do is we would have a class where you're doing filtration and evaporation, and I will run a distillation up on my desk. And so the idea is that you come up and check that you can see the condenser working, and we normally start with a certain volume of like immiscible liquids, and then see what's left at the end so you can see that they've separated and all that kind of stuff. Okay, so we would have done both of these. Okay, so I'm just going to go into this and we'll have a quick look. it go on a little bit, so I'm just going to skip.
Now we will add 1 teaspoon of sand to the 2 teaspoons of salt. To the side, don't mix it yet. Okay.
Okay, so she goes on here, I've watched this, she goes on here and she gets them to taste them, like taste the salt and taste the sand and then feel their textures and stuff. So I'm just going to skip to where he starts mixing them.
Worse, like salt, but we have salt that is thicker than the sand. So we will be, it's white, and the salt and those are slightly larger than the mixture.
Okay, so
where you just have them both together.
I know what it looks like. It looks like snow on dirt.
It looks like snow on dirt. Okay, now we are getting 100 milliliters of water and pouring it into the sand and salt mixture. And we are going to stir it for 1 minute. So go ahead and stir it. You might want to set a timer for 1 minute.
So you can see almost instantly as you pour that water on that the salt has dissolved, but the sand is clearly not dissolved. Okay?
Stir until that salt dissolves in the water. You will notice that the sand is not dissolving. Okay, after stirring for 1 minute, you want to put the filter into the funnel and put the funnel on top of the mason jar or drinking glass. Okay, so put it on top of there. Now, Nathaniel, go ahead and pour the mixture through, and Rachel, hold on to the funnel. Hold the funnel while he is pouring. Pour slowly, slowly into that filter. Okay. As you can see, the water is going through the filter and the sand is not. Okay.
So sand is an insoluble solid. It did not dissolve. So the best way of separating an insoluble solid from a liquid is to use filter paper. So the filter paper is catching the sand, and what's going through does not contain any of that kind of, I mean, it's quite a brown, like a dark colour, and it's not going through.
Okay, so it's dripping down into the mason jar. And something has probably gone through this filter paper. What do you think is going through the filter paper besides the water?
Salt?
Yes, the salt has been dissolved in the water and is now able to pass through the filter like magic.
So not magic, science, because salt is a soluble solid, so it is dissolved in the liquid. Filtration will not remove soluble solids, and it will only separate insoluble solids. Okay, so yeah, it's actually a lovely experiment, but not magic.
And then when you dehydrate the water, all that's left is just the salt.
Yes. So as soon as that stops dripping, what you're going to do is you're going to pour the mason jar into the pie pan. As soon as all the water has gone through the filter, and actually not all the water has to go through the filter if you're in a hurry, then put that to the side, maybe on top of the beaker or something, and then pour the mason jar water into a pie plate. Okay, it could be an aluminum pie plate. We have a glass pie plate. And what you're going to do is you are going to leave that out for a few days, and you're going to wait until the water evaporates, and then we will see what is left at the bottom of the pie pan.
So, like I said, I wouldn't use this type of evaporation method because it would be difficult in the lab. It would mean we'd have to like leave a load of beakers there for probably 6-7 days. Like, it would just be annoying. So at this point, we would help the process along by using the separation technique, evaporation. Okay, so it doesn't make a difference that they've lost their water as well, and we're going to lose our water. So when you evaporate, whether you allow the process to happen naturally or you heat it up, the solvent is lost. It turns into water vapor and it's gone, and the salt should be left behind. So you can see that here.
After a few days, the water has evaporated and salt crystals are left behind.
Okay, so that's these two kind of done in one experiment, and like I said, we would have done it similar to that. Yeah, that's pretty much what we would have done actually. We would have used sand, salts, put them all together and used both processes. Like I said, I could have separated the salt and water mixture using the Liebig condenser. I tend not to do that, like I said, because it's very hard to clean the bottom of the round bottom flask from the salt. And so we probably would have done the miscible liquids. Okay, but hopefully that's okay. Next thing here is chromatography. So chromatography is used, get my pen. It's used to separate mixtures of substances that are in solution. The different substances are carried up a piece of chromatography paper by the solvent at different rates. So really what we generally do with this one is a marker, so the colours in a marker, and they're carried up the paper. So I'll just show you this one, and like I said, hopefully if we're back to normal in September we can do these two.
This video shows an example of a chromatography experiment. The goal of the experiment is to separate the different pigments of ink which are present in a wet erase marker, which we'll see right here. So a vis-a-vis marker is wet erase, which means that the pigments are water soluble. We'll start our experiment by drawing a line with the marker on the chromatography paper. Then what we want to do is insert that chromatography paper into a beaker with a small volume of water in it.
So what you want is that you notice he drew his line about 1 centimetre off the bottom of the chromatography paper. Essentially what you want is that you dip the chromatography paper into the water below that line. Okay, so you don't dip the line in, you dip below the line. So that's what the centimetre is for. That centimetre of uncoloured chromatography paper is the bit that gets wet, and then the water is carried up the chromatography paper. Okay?
We can see that the water will start to rise up the chromatography paper because of capillary action. You'll note this happening very quickly because this is 16 times speed playback. We can see that the ink, which originally looked black, is starting to separate into different colors. This is because the different pigments have different properties. Some of them are heavier, some are lighter, some are more soluble in water, some are less. Because of these differing properties, all of the different colors are going to travel at different speeds. And by the completion of our experiment, we should see some very nice separation of the different pigment colors. Now, to do analysis of our results, what we're going to want to do is to measure the distance traveled by each pigment. Let's pause here for a moment. So I want to measure the maximum distance traveled by the water and then by each different pigment starting at the line drawn on the paper. To be fair, we should be comparing the distance traveled by the water starting from the same point where the pigment started traveling. So we'll measure all of our distances starting at this point. Looks like the maximum distance traveled by the water reaches about to here, and then we can measure the maximum distance traveled by each of the different pigments. Let's continue our playback.
Okay, so he goes on then to do a calculation that I'm assuming is a Leaving Cert Chemistry calculation. I don't even know if it's on the Leaving Cert Chemistry course because I haven't seen it before. So that's the experiment you do. So you take your marker, you draw your line, and you allow it to separate, and then you go and you measure this colour travelled this far, this colour travelled this far, and so on. And normally because it doesn't take, I know that he had that in massive playback, but it doesn't, like, it doesn't need a lot of equipment, it doesn't take a lot of time. So normally we do a couple of, so you might do like a black marker, a blue marker, and a red marker, and see what they separate to. So that's chromatography, to separate mixtures of substances that are in solution. Okay, so the black marker was a mixture of a load of different pigments. They're all water soluble because they were water based markers, so they're designed to vanish, I suppose, when they're designed to react when you apply water to them, and that's why they're removable and stuff like that. So when you apply like water to them in this way through chromatography paper, they come out as solution. Okay, which is quite nice. Liebig condenser and distillation we've talked about. Okay, this one I might do. I think it's kind of obvious, but anyway. So magnetism can be used to separate if one of the substances is magnetic and one isn't. Okay, so if you've two substances mixed, I don't know, sand and like we've loads of iron. Oh, that's actually what they do: sand and iron filings. Okay, so if you mix up sand and iron filings and you go and get a magnet, the iron filings are magnetic, so they will be attracted. They'll be attracted to the magnet, and the sand won't. So you'll have separated. Okay, so quite a simple idea there. Separating immiscible liquids. So we talked about miscible liquids up above. So these are immiscible, which means they don't mix. So immiscible liquids are liquids that do not mix. Okay, so oil and water would be a classic example of substances that don't mix. Okay, so they have different densities, so they don't. The more dense one will drop to the bottom, and the less dense one will sit on top. And there's a nice experiment. I say you probably did it in primary school, where you can get a couple of different ones, and you get like 4 or 5 different densities, and they all just sit on top of each other. So to separate these, it's quite a simple process. Essentially, so this is oil and water. You would put the mixture of oil and water into a separating funnel. Okay, so you throw them in and you would leave it for like a day to fully separate. Okay, so to allow them to settle and allow that oil to take the top layer and the water. So now what you should have down the bottom is only water, and your oil is sitting on top, and you've just a little like tap here. It's called a stopcock. It's just a little tap. So you literally turn it and it opens. So if it's perpendicular, it's open, and then when it's in line with the funnel, it's closed. So you would turn it, and the only thing that comes off is the water. And you'd be able to do that, like, really close to, if you were good at it, you could get it right up here, really, 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 really close, to let all that water off. And you'd start running the risk when you get really close to that line that you're going to let some oil in. But yeah, so that's immiscible liquids that don't mix. You literally put them in the funnel, allow them to separate over a couple of days, and then you just pour off. Like, you're literally just opening the tap and allowing the water to drip out. Okay, so they're your separation techniques. Like I said, I would definitely do the Liebig condenser, but it would be a demonstration happening on my desk. We might do the magnetism one. It's very straightforward, and it's messy. So we think about that one. The immiscible liquids, it takes so long, but again, that would be one I could do as a demonstration. Like, I could set it up, say if it was this year, I would have set it up on a Friday and have it sitting on the desk for 2 or 3 days. So you could see the separation, and it would pour off a bit of water. Okay, so again, we just wouldn't do that altogether because it takes too long to allow the settling to happen. But pretty much all of those we would do in some vein. And you would, like I said, would do the top few there, so they'd need to be written up. So that's what we're going to start with in September. Right, so just this last part now, just moving on. So fractional distillation. So we talked about distillation there, where you boil and then it's trapped. So you boil something, the steam is trapped and then it goes through the Liebig condenser and it's condensed back to being a liquid. So you can do what's called fractional distillation, where you're separating a load of different things based on temperature. Okay, and they use it for crude oil. So it does say it down here, but the main thing that crude oil is known for is that it's the raw material in a lot of things, but it's definitely the raw material in making plastic. Okay, which is quite topical at the moment. So it's a thick black liquid found in beneath the Earth's surface. It's not very useful. Crude oil, when it's not distilled, it's not very useful. You can't really do a whole lot with it. It's a mixture of many different products that are only useful when they're separated. How is it separated? It's separated using fractional distillation. Okay, so crude oil, which is only useful when all the products are separated, and it's separated, so it's a mixture. I should put that in. It's a mixture, and it's only useful when all the products are separated using fractional distillation. So they heat it, and they heat it enough that it turns into a gas. Okay, and they put the gas, you can see the tower over here, into a large tower. Substances with high boiling points turn to liquid at the bottom, and then as it goes up, the gas cools, and you have liquids or substances with low boiling points turn to liquid at the top. Okay, so if it's a gas and a gas with a high boiling point, let's say it's going to change. Like water's boiling point is 100 degrees Celsius. That means at 100 degrees Celsius, it goes from water to steam, but it also goes from steam to water. That's where that change happens in either direction. Yeah? So what we have is down the bottom here. So this is, it says it goes in at 400 degrees Celsius. So it goes in as a gas at 400 degrees. 340 is the magic number here for this residue, which means it doesn't have to cool very far for this to become a liquid. Then it cools a bit more down to 260, and 260 is a magic number for diesel. And then cools a bit more to 180, which is the magic number for kerosene, cools a bit more, and so on and so forth. Okay, so they call it the boiling point, but remember that the boiling point it's in two directions. Like that when they talk about boiling point, they mean water to steam, but they could also be talking about steam to water, and in this case they are. Okay, no, I shouldn't say steam and water, I should say gas and liquid, but you know what I mean. Okay, so that's how it works. And then, like I said, one of the things that they make, that crude oil is used to make, is plastic. So plastics are, would you believe, only around since the 1930s, and they are absolutely phenomenal and amazing and have such an unbelievable range of uses that as a product that somebody manufactured, it was a game changer. But there's clearly a problem. Okay, and the big problem is that plastic is not biodegradable. Okay, so biodegradable means that it can be broken down by bacteria and fungus. So do you remember we talked about bacteria and fungus and how they feed on dead plants and animals? Okay, and they process the dead plants and animals, and that's biodegradable. Biodegradable is when fungus and bacteria can feed on it and process it. They can't feed on plastics, so they can't be broken down. So essentially the first plastic bag that was ever made back in 1930 is still here somewhere. Every single bit of plastic that has been made since the 1930s is still here. Okay, so that's a problem. And what I said at the start, which is that they're phenomenal products and they're so useful and blah, 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 is true. But it's almost to its detriment because we can't live without it. And it's a big problem at the moment. Okay, so all different types, so polythene, PVC, polystyrene, nylon, flexible, strong and inexpensive, plastic bags, lunch boxes, weather resistant and strong, gutters and window frames, rigid or foam, food containers, and can be spun into fabrics, carpets, tights, ropes. Okay, so there's loads of uses of plastics. So the raw materials for plastics are separated from crude oil by fractional distillation, as we talked above. When they separate them, they separate them into what's called monomers. The word mono means one or single, okay? But then the monomers react together and they create long chains called polymers. And the word poly means many. Okay, so the couple of monomers come together and they make polymers, which is why if you look at the names, a lot of them, that's polyvinyl, I think it's chloride, I'm not sure, but they're all polys, and this is why, because they're made of polymers. And so they start as monomers when they go through fractional distillation, then the monomers all react together and you get this long chain of polymers. Okay, I talked about this here. Plastics are not biodegradable. This means that bacteria cannot break them down. The only way to actually get rid of them is to burn them. But if you burn them, they release poisonous fumes. So that's not great either. So there are, like, most plastics are recycled now, and scientists, like, this huge amount of money we put into kind of a reuse of plastics, or a way of breaking them down. So there actually are things called biodegradable plastics at the moment. Problem is, to make them, you need incredibly high energies, which requires a lot of carbon dioxide, because you have to burn fossil fuels to do that. So there's a bit of a toss-up. So they haven't solved the problem. It is a massive problem. They need a replacement. They need a replacement that's as good, because there's no way people are going to accept, like, you know, I suppose, a replacement that doesn't work as well. Like, if you take, like, they're in your window frames, like, there's no way people are going to accept a replacement. That means your house goes back to being drafty, you know, things like that. So whatever they replace it with is going to have to be as good, but is going to have to be a lot more environmentally friendly. And then obviously all the plastic that at the moment is in our oceans and just basically, like, choking the earth, that we're going to need to come up with something to do with them. Okay, so a few problems. And just a quick note on fracking. I don't know if you've heard about it. Natural gas is usually extracted by drilling through rock to get to an underground well of gas. Gas comes to the surface very easily because when you drill through, it's at really high pressure and it wants to release that pressure. So where it is contained is incredibly high pressure, and then as soon as it gets the opening, it flies out of the opening because of the high pressure. But again, this is all very recent. They've discovered that a huge amount of natural gas is trapped in kind of on the way down, I suppose. And collecting natural gas like this is not easy. It's not as easy as it is from underground because there isn't that high pressure. So they use a method called fracking, which is hydraulic fracturing. And so what they do is they drill down into the earth and they inject a mixture of water, sand and chemicals into the rocks at high pressure, which releases. So it's literally like kind of giving it a push. They inject it in and they force the gas out. It's quite a controversial one. If you have any interest and you want to look it up. So we have some advantages and disadvantages. Obviously there's stores there that if they don't do fracking, they're just leaving behind. It releases natural gas methane, which is the least polluting of all the fossil fuels. So it's better than another one, I suppose. Provides a fuel source alternative. So obviously we're quite low on sources of energy at the moment. So a lot of people believe that fracking could release some gas which would buy us a few more years to try and come up with renewable sources of energy. The disadvantages are large amounts of water are needed for the process, so that's obviously not particularly environmentally friendly. Fracking may result in small earthquakes because you're literally, like, the hydraulic thing, like, it's a vibration kind of to drill into those rocks. And natural gas is obviously, I mean, it's not a solution going forward because it's still non-renewable, it's still natural gas. Okay, so just a quick note on that. You wouldn't need a whole lot on those last few bits, just kind of a general idea of what they are. Okay. Yeah, so that's it. So I'm not going to give you any homework. Just take down whatever notes you need from here and get studying. I have a class, so where did I put it here? So Higgins Science and Maths, that's 12 o'clock on Wednesday, and Robinson Science and Maths is 12 o'clock on Thursday. Okay, so no pressure, it's literally just if you have a few questions to ask, we'll go in and do that there. I'll do my best to obviously answer any questions on the spot. If there's anything that I'm not sure about or I need to check with Miss McDonald or anything like that, I'll get back to you. So I'll make sure I keep notes. So yeah, so that's it. Obviously pop on tomorrow if you have any questions that you want cleared up before the exam next week. Even if the questions are about the exam, whatever it is. And like I said, no homework, so that's it. That's the content done. That's what we're covered this year. And yeah, so I'll chat to you tomorrow if you're on, and if not, the best of luck with the exams next week and have a great summer.